Yongxin got his PhD from the University of Minnesota with Trifon Giorgio. And then he did a postdoc for in medical imaging related work with Alan Tannenbaum. And then was at Iowa State for 1 year before he moved to Georgia Tech. He's won several awards for his sort of fundamental work, the Axelby Award and the Scion Control Award for Best Papers Award. And some of you who may have been at the ACC in San Diego 23 maybe heard him give his very nice plenary, which was very interesting to me. But today he's going to talk about something different, and so we're looking forward to it.
Okay. Okay, good morning, everyone. Thanks for the invitation, and thanks for the introduction. So it's really a great pleasure to be here, first time in the Santa Barbara. Very nice. So today I'm going to talk about something new for our group. It's about the safety of stochastic system. It's about 1.5 years old for our group. So this talk is going to be based on joint work with Saber, who used to be here for quite a long time, and now he is at the CU Boulder, and the two of my PhD students. Okay. And these are the two papers I'll be focusing on throughout this talk. The first one we released this in 24, and the second one is relatively new. It just we released this last month. So safety doesn't need a definition, right? It is clear what we want. So it plays a very important role in many applications, specifically whenever you have a human involved in the loop, right? Safety is very critical. So I'm going to skip these slides, but it's clear why we would like to make sure safety. So there are many challenges remain to be resolved if you want to ensure the safety of autonomous system. So here I list a few that are most relevant to this talk, but there are many more. Okay. The first one is very often you have a large number of agents. Okay, so not just one agent, you have many of them, like autonomous vehicles. And very often you would have high dimensional state, not just first order integrator or second order integrator. For instance, for humanoid robot, you may have 30 degrees of freedom or even more than that. Okay, and then very often you have nonlinear system. Okay, that's add some additional complexity. So all of this asks for a very scalable algorithm. You want an algorithm that is scalable to all of this setting. And another source of complexity comes from uncertainty. So if there is no uncertainty, things becomes a little bit easier because you can simulate, you can basically predict exact future. Then it's much easier to do safety verification. But in reality, you always have uncertainty, and this is not, you cannot predict the exact future. So therefore, you need some very effective algorithm to account for this uncertainty. So this is another source of complexity. So control theory has a lot to offer in terms of safe autonomy. So here I list the two of them, which is most relevant to this talk, and also the most classical ones. So the first one is barrier function. So barrier function tries to ensure safety by forcing the safe set to be forward invariant. So this means if you start from this set, you would stay here forever. Then of course you can be safe, right? Then another one is reachability analysis. It's based on a very different strategy. Basically, in reachability analysis, what you do is you predict all the possible future approximation of this, right? Like what you see here. If all the possible futures are safe, then you are safe, right? Very different. These are two different strategies, but both of them would work. So this is how barrier function works typically. So you have a safe set, which normally is defined to be a level set. Okay. Then let's say you have a dynamic system, and let's say no control at this point. Okay. So then, if you can make sure that this inequality holds, this is a special case. If you can make sure this inequality holds, then you can ensure that this set over here is forward invariant with respect to this dynamics, which means if you start from a point in the set and you follow this dynamics, you're going to stay there forever. Okay? You can also put some control in it. So if you have some actuation, then basically what you need to do is if you can make sure this inequality holds, so there's a maximum here, then this means there exists a control strategy that can make sure the system is safe. So this is the control barrier function, which is really quite popular these days. And based on this, this is a very typical quadratic programming-based safety critical control strategy. So normally what you do is you have some baseline controller, then you filter this control, so you perturb this control a little bit to ensure that this set is a forward invariant. Okay, so this is a typical barrier function pipeline. So how about the reachability? So reachability is like this. So basically, let's say you have this is your state space, then you have some initial configuration, then you simulate the possible trajectories of this system according to different initial configuration. Then if you do this many times, then you can have a very rough estimation. Basically, it's a set so that all the possible trajectory has to reach there. Okay. Then if you can make sure this set doesn't intersect with this unsafe area, then you are good, right? Because this basically makes sure every simulation or every possible future of this dynamic system is going to be safe. It's going to stay away from the unsafe set. So this is the two strategy, barrier function and the reachability analysis. And as I mentioned earlier, one source of complexity in safety and verification is induced by uncertainty. So what is uncertainty? So in control community, there are two types of uncertainty normally we consider. One is called the deterministic uncertainty. Another one is called the stochastic uncertainty. So what is the deterministic uncertainty? Deterministic uncertainty normally is assumed to be bounded. Normally what you care is the worst case performance. And you don't assume you know the statistics. You only know, okay, it's bounded. So you know the bound. Other than that, you know nothing about this. And this is the typical uncertainty you use in robust control. Okay, if you are taking robust control course, you should know this. And another one is stochastic uncertainty. It's it's like a complement of this one. So in stochastic uncertainty, what you consider is average performance, because the worst case performance is really bad, because very often, like if you have Gaussian uncertainty, it's going to be unbounded. If you consider the worst case, it's going to be, you cannot get anything reasonable. And stochastic uncertainty, you have statistics. And normally, if you think about discrete time system, you would assume every time instance, the uncertainty are independent from each other, which is a very reasonable assumption. And this is a very typical uncertainty considered in stochastic control. Okay, so these are the two major types of uncertainty. So the goal of this talk is to provide an effective and scalable algorithm for safety verification for general nonlinear system and both stochastic and deterministic uncertainty. So this is what I want to achieve in this talk. So I want to emphasize we consider both deterministic uncertainty and the stochastic uncertainty, and we consider general nonlinear system. And we would like the algorithm to be effective and also, more importantly, scalable. So I want to scale to, let's say, 100-dimensional system or 1,000-dimensional system. That's what my goal is. And specifically, this is the dynamic system I will be considering. So the first one is a stochastic differential equation. So this is just really a differential equation driven by some white noise. So this dW is just Brownian motion. So this x is the state, and the dt here represent deterministic uncertainty, and the dw here represent the stochastic uncertainty. Okay, so in this talk, I would only focus on the continuous time dynamics, but everything I discussed in this talk can be easily extended to discrete time system, or which is given in the paper, but I would skip this part. So this is the problem setup. Okay, let's move on. So our approach is based on reachability analysis. So this is the outline of the rest of the talk. I will try to finish. Normally, I can finish the first part for sure. Let's see if we have time for the second part. So let me start with the reachability analysis for stochastic system. So what is the reachability? So this is a typical definition of a reachable set. Many people may know of. So this is for deterministic system. It's a very clean definition. So you have a system which looks like this, and you have some initial set, okay? And you have some disturbance, which is deterministic disturbance, because this is a deterministic system. Now, the reachable set at one time point t is denoted to be all the possible value of the state at that time, given that you start from this initial set, and given that the disturbance has to belong to this disturbance set, okay? So it's just an envelope of all of this possible xt. And this is a very clean definition, and but this definition very often is too conservative for stochastic system. So why is this the case? Because normally this definition over here assumes this set to be bounded. If this is not bounded, then you're not going to get anything meaningful. So a very simple example is the simplest stochastic system is the Brownian motion, okay? So if you consider this, if you use this definition here, because the Brownian motion is unbounded. So if you use this definition, the only thing you can get is the entire space. So your reachable set is always the entire space, no matter what you do. So that is not very meaningful if you want to do any meaningful analysis, right? So therefore, we need something better for stochastic system. So this is the typical choice in the literature, and this is also the choice we would use. So it's a slight modification of the reachable set. So you still have some initial configuration, which is fine, because we consider both deterministic and stochastic uncertainty. We consider we still have a deterministic uncertainty, which is okay. So the major difference is here. We have a probability value here, which is something between 0 and 1. And we call that a set is a delta probabilistic reachable set of this stochastic system at the time t if for any initial value and any deterministic disturbance, the probability of xt belongs to this set is greater than 1 minus delta. Then I would say this set is a delta probabilistic reachable set. And normally in practice, you would like delta to be very small, 10 to the power minus 3, 10 to the power minus 10 even, depends on application. So this is the definition of a delta probabilistic reachable set. This is the reachable set definition for stochastic system. Okay? So there are many algorithms people have developed trying to estimate, because in reality, there's no way you can compute this set exactly. Okay? So you have to find some way to approximate this. So there are many approaches. For instance, some people use pure Monte Carlo. That's very expensive. You can also use HJB-based equation. That's even more expensive. Okay? So there's some method, but they are not quite scalable. We would like to develop some scalable algorithm. So therefore, we use a strategy which is very different from literature. We call this strategy separation strategy. Our intuition is very simple. So we care about this, oops, where's my mouse? We care about this stochastic system. So now if I remove this disturbance, then I have a deterministic system. Okay, if I assume then start from the same initial condition and driven by the same dt, the deterministic disturbance, right? Then you can imagine what is going to happen is the stochastic trajectory is going to fluctuate around the deterministic trajectory, right? Especially when the noise is very small. So that is the intuition. So this means that you would expect xt minus xt to be relatively small. Okay? So to make this more formalized, so we have this separation strategy. So if you can make sure this is what we define associated trajectories. If you can make sure this distance is always less than this number with high probability, okay, then what you need to do is you just need to approximate the reachable set of the deterministic system over here. Then you can easily conclude that the summation of this set and this ball with this radius is going to be a delta probabilistic reachable set of the stochastic system. And this is basically the intuition. So this is a simulation of the stochastic trajectory. It's going to stay very close to the deterministic one. If I can make sure the deterministic trajectory has to reach this area, then I just need to make this set a little bit larger, which is the summation of this one and this ball. Then you can make sure the stochastic trajectory is going to reach this set. So this is the basic intuition, very simple intuition.
Can I just clarify? You're
Yeah.
fixing the disturbance for every sample path. I mean, the disturbance is the same for every sample path. Is that correct?
No, the disturbance is not the same. So here, when we define the associated trajectory, we want to make sure they have the same deterministic disturbance.
Yeah, so that's my question, right?
Yeah.
You're not like taking it to be adapted to the solution, the information that's evolved.
No, we assume them to be the same.
It's the same.
Yeah, we assume they are the same, they are given, but they can be arbitrary. That's, yeah.
Sure, but
Yeah.
it's the same for every sample path.
Not for every sample pass. Yeah, it's basically the same for every sample pass, I would say, because that is used in the definition also here. Yeah, that's a good point. Any questions?
Yeah, like let's just say I'm just trying to understand, like for chaotic system, does that
Yeah.
mean your ball is really large?
Yeah, the ball is going to be really large, so it depends on your system.
Okay.
Yeah. So, yeah, that's a very good observation. So we will see assumptions we would impose to make sure the ball is not that large, and which is not very strict assumptions. Yeah, definitely we are not considering chaotic system. We are considering more reasonable system. Okay, so this is the strategy, and based on this strategy, our problem of estimating the reachable set for the stochastic system becomes this problem here. So basically what we need is we need to find this bound, which is this value here, such that this value, this xt minus xt, the distance, is bounded by this value with high probability. So this is really the problem we address in this part of the talk, okay? So we want to quantify the deviation or the fluctuation of the stochastic trajectory from the deterministic counterpart. Once you can do this, then you can adopt this separation strategy to have a very good estimation of the reachable set for the stochastic system. Okay, so this is what we do. So how do we solve this problem? How do we quantify the distance of two systems? How do we quantify the distance of two trajectories of different systems? Why? Well, most widely used approach is this contraction. I think many people here are familiar with this, so that's good. So this is just a quick recap. Contraction theory, right? Okay, so what is based on some matrix measure. It's just some definition. Let's not worry too much, but it gives you some property of the dynamic system. So normally you assume C to be less than or equal to 0, but C doesn't have to be less than or equal to 0. So in this paper, we assume C can be any numbers. So of course, when C is less than or equal to 0, it's better, but it can take any values. So I would say almost any dynamic system would satisfy this assumption. It's just a matter of value of C. Sometimes C can be bad, so you cannot get a very good result. Okay, if a system satisfies these assumptions, one of them, then we say the system is contractive. Then under this assumption, you can quantify two trajectories of this system in this way. So basically, this tells you the distance between these two trajectories is going to be bounded by this value here plus some multiply the initial distance. Okay, and the proof is very easy. Just use this energy function. You take a standard Lyapunov analysis, you get this. And as you can see, if C is negative, then you see they would actually collapse to one thing. So that's its kind of stability. But even if C is positive, this will give you a good estimate to see how fast they would diverge, right? So that's good. So this is for deterministic system. So what we want is we want to analyze the distance between a stochastic trajectory and deterministic trajectory. So can we extend this analysis there? Oh yes, very simple. So this is my stochastic system. So I'm going to assume this part satisfies this contraction assumption. But I'm going to have another assumption for the noise part just to make sure the energy of the noise is not infinity. Very mild assumption. Okay. Then already a long time ago, people have already discovered that if you use the same energy function, and you can make sure that the associated trajectory of stochastic and deterministic system satisfy this calculation here. And after you do everything, you find out the expectation the MSE, the mean square error of these two, has to be bounded above by this number over here, which depends on the value of C and the energy of sigma and also dimension of the problem and the T. Okay? So this is what you get. And because what we really want is we want to make sure this is less than or equal to something with high probability, you can apply Markov inequality. So eventually you get this. The probability of this distance to be less than this value is going to be greater than 1 minus theta. Okay? This is what we get. Okay, that's great. Okay, so it seems the problem is resolved. But is this true? If you look at this result, you see this is not a very good result. Why isn't this a good result? So as a question asked earlier, right, what we want is we would like to make sure this number here is small. Right? If this is large, then it's useless, because if this is the entire space, what is the use of that? We want this to be small. Okay, let's consider one setting where theta is 10 to the power minus 10, which is typical in aerospace application. What is going to happen is this is going to be around the 10 to the power 5. That is something which is too large, is completely useless. Okay. So if we follow this analysis, we get something, but this is not very useful. So the question we ask is this the best we can do? Can we improve this result, make it tighter? Okay, so when we first asked this question, the first attempt is, if you want to ask this result for nonlinear system, whether this is the best result you can get, the first thing you will try is what? You will test this in linear system to see whether this is tight for linear system. So this is exactly what we did. So we cook up this very simple linear system, and this is the deterministic counterpart. Then if we apply the result we just got, we get this result over here. I just reload this result. But for linear system, we have something really nice, right? We know xt is Gaussian. Okay? And the covalence you can actually compute. You compute the covalence, it looks like this for this very simple system. So what's so nice about Gaussian distribution? Everyone knows the distribution for Gaussian, right? The density decays like e to the power minus x squared. This is what? This is a very fast decay. So thanks to this fast decay of the density, you can actually say that, compute that the probability of this to be less than this value is greater than or equal to 1 minus theta. If you compare these two results, what we get for linear system and what we get for nonlinear system, there's a huge gap. Why? Because this one has dependence square root of 1 over log theta, where this one for Gaussian has a square root log 1 over theta. These two are completely different. So let's say the example we gave earlier, if theta is 10 to the power minus 10, then this number here is about 10 to the power 5, where this linear system, what you get is about 5. So this is a huge gap. So this result is useful. This result is not, if you really want to do verification. So this is good. So this at least means the nonlinear analysis we got earlier is not tight for linear system. Okay? But maybe it's tight for nonlinear system, right? But if this is the case, then this is horrible because there's no pure linear system in reality. Every linear system has a small nonlinear perturbation, right? So if this is the best you can do for nonlinear system, then you can only get the worst result. Okay, so what we want to do is we would like to develop a result for general nonlinear system which is as good as linear system. That is our goal, and we accomplish this goal. So how do we do that? So clearly we cannot use Gaussian distribution. It's very special to linear system. The moment you have a nonlinear factor, nothing is going to be Gaussian. So what is the next best thing? Sub-Gaussian. Okay, so this is some background on sub-Gaussian distribution. What is sub-Gaussian distribution? Sub-Gaussian distribution is a random vector. It's said to be sub-Gaussian with some covalence. This is theta squared. If this random variable satisfies this inequality, which is the moment generating function, is less than or equal to this for any lambda and any L on the unit sphere. So this is the standard definition of sub-Gaussian. is a generalization of Gaussian, and it includes Gaussian and many other distributions as a special case. Okay. And what's good about sub-Gaussian distribution is that sub-Gaussian distribution enjoys exactly the same concentration as Gaussian distribution. So whatever you can say about Gaussian distribution, you can say the same thing for sub-Gaussian distribution. Specifically, for a sub-Gaussian distribution, you can say the norm is less than or equal to this value with high probability, which again has square root log 1 over delta dependence, which is exactly the same as Gaussian distribution. Okay, you don't lose anything. Okay, so that's good. So this means if we can prove xt minus xt, which is the term we would like to bound, is a sub-Gaussian, then we are good to go, right? So that's the idea we tried. Unfortunately, this is not true because xt minus xt is not sub-Gaussian in general. Okay. So the secret weapon, okay, of this line of research is this moment generating function we call average moment generating function, which is really interesting. Is really, what is the average moment generating function? It's really just if you forget about this term, this is just the moment generating function. But what we do is we just take the average over all the vector on the unit sphere. Okay? So bounding the average moment generating function is much easier than bounding the moment generating function. Because if you look at this, if I want to bound this by this value, I want to make sure this is true for every L. But here, if I want to bound this average moment generating function, I just need to bound the average of them. You don't need this to be true for every L. Okay, it's a much relaxed assumption. Okay, so this very interesting function was first developed a few years ago by this paper in a very different community. Okay, so but what's good about this this AMGF is that if the AMGF is bounded above by this value, then you can get exactly the same concentration property as the sub-Gaussian. So basically, you can view this as a relaxation of sub-Gaussian distribution, but shares exactly the same concentration as the sub-Gaussian. Okay, so we couldn't prove xt minus xt to be sub-Gaussian, but we can prove xt minus xt is a relaxed sub-Gaussian. That is what we accomplished. So I'm going to skip the proof. If you are interested in this, you can look at the paper. Not very technical at the moment that you have this definition. What we get is because we prove this roughly, then we get xt minus xt, the norm is actually less than or equal to this, which is exactly the same as what you get for the linear system. So this is as good as the linear system. Okay, so and this has a very good dependence on delta, and it's actually optimal. So this figure here, just to show you, this is the optimal. You cannot get a better bound than this under the same assumptions. And this dependence on the dimension and the square root of log 1 over delta is also optimal, which we can verify this theoretically, or you can verify this through large-scale Monte Carlo simulation. You cannot do better, okay? But we give very explicit formula for this. And with this, we provide a general recipe for reachability analysis for stochastic system. And this is how you do it. So what you need is you need to have a reachable set for this deterministic system. You can choose whatever method you prefer. That's fine. We don't have any restriction on that. Then you can say that the probabilistic reachable set of this stochastic system, estimation of this is going to be a summation of this deterministic reachable set and this ball. And this ball, the radius is just given in this closed form expression. Okay, so in practice, you can choose what method you would like to use to estimate the deterministic reachable set. Like if you care about scalability, you can use contraction-based, interval-based. These are scalable algorithms, can scale to hundreds and thousands of dimensions of system. If you care more about the accuracy, you can use the set propagation, HJB-based. I mean, all of these are for deterministic system. So there are many methods that are available. So what we did is really we reduce a stochastic problem into a deterministic problem, and we give you exactly the general recipe. Okay. Okay. So that's about the reachability analysis. How much time do I have left? Plenty of time. Okay. Okay, that's wonderful. So so I went a little bit faster because previously I couldn't finish this.
Can I ask you
Yeah.
a follow-up question to
Yeah.
the previous one? So your first analysis, which was conservative, was Lyapunov based, and it's my understanding that with that tool, you're able to say more than just that you get this behavior for a disturbance that's the same for every sample path. You can get it to hold that you get that result for disturbances that are adapted to the information that evolves. My question is the proof technique for the less conservative result also Lyapunov based, or might it be that this change from the conservative bound to the less one is moving from one larger class of disturbances to a smaller class of disturbances?
No, it's the same. So this that's a great question. So I skipped the proof, but you can say it's also Lyapunov based. So the only difference is instead of using the quadratic Lyapunov function, we use this AMGF as the new Lyapunov function. But all the others are the same. So you don't lose anything, but you just get a better result.
So then don't you think you can make the statement that you're getting this not just for disturbances that are the same for every sample path, but for disturbances that are adapted to the information?
I think I need to think about this. So one small problem that we are not so sure is that depends on what adaptive we mean, right? So for instance, if D is a function of X, okay, let's say this is one of the case, then what happens is that when we compute this contraction rate, we have to take into account that part. So which means this is going to change this contraction factor. So that is one thing we are not so sure. So other than this, I think everything is okay. Yeah. Yeah.
Understanding the presentation of the question, I think because the analysis performed on the reachability set accounts for any deterministic disturbance and any stochastic disturbance, that includes ones that would be like aware of stochastic disturbance, right? No.
So maybe we can postpone the discussion for after.
Okay, sounds great. That's great. So this is about the reachability analysis for stochastic system. So now let's get into the real problem we would like to solve. It's the safety verification for stochastic system. Okay, let's take another look at this problem we care about. Okay, so if you think about the safety, right, especially if you just think about safety, right, what do you really want? Let's say this is the unsafe area, obstacle. You have a robot here. Due to uncertainty, and also initial set value, when you simulate this, you would have all different trajectory, right? That's true. Right? If I want this to be safe, let's say with maybe 1% safety guarantee, then what I really want is if I simulate this 100 times, right? At most one of them would fail, right? So which means at most one of the trajectory is going to overlap with this unsafe set. Okay, so this is slightly different from the probabilistic reachable set, because the probabilistic reachable set only tells you that at this time instance, okay, the approximation of the reachable set is in this area with high probability. So now, if I want to make sure safety, I would like to make sure that in the trajectory level, I do not intersect with this unsafe area. So this is not a problem for deterministic system because they are roughly the same. But if you are talking about stochastic system, there is a huge difference. Because if you want to make sure my trajectory doesn't intersect with the unsafe area, I want to make sure at every time instance it doesn't intersect. Like when you calculate the probability, it's a completely different probability. So even if you can make sure at every time instance you do not intersect with that area with high probability, you cannot make sure that the trajectory doesn't intersect with that area with high probability. So there's a small difference, which is really due to stochastic uncertainty. Okay, this is a very tricky difference. We didn't realize at the beginning, so that's why we did this reachability analysis. But this is very important. So we have to get trajectory level safety guarantee for safety verification. So how do we do that for stochastic system? So the only tool I'm aware of is this martingale inequality, okay, which is a very beautiful inequality I will just explain. So what is a martingale inequality? It's a very powerful tool in stochastic system. So it relies on this definition of non-negative martingale. So which is a random process, okay, stochastic process, less MT. So we say a stochastic process is a super martingale if the expected value of the future is less than or equal to your current value. Okay? Then it turns out if you can have a super martingale, then you can actually bound the trajectory level. So you can quantify that the probability of this maximum of this martingale over the entire trajectory greater than this value is less than this. Okay, so this is the only tool I'm aware of that can give you trajectory level guarantee, probability guarantee. I think a very easy, very intuitive way to explain this super martingale is so what is the most well-known martingale? The gambling, the amount of money you have, okay, if you go gambling, okay, because if it's a fair game, so most likely the expected value of the money you have in the future is going to be less than the money you have now. So this inequality tells you don't rely on gambling because the probability for you to, let's say, double your money is like at most 50%. Triple your money is like 30%. Okay? If you want to make money 100 times, the likelihood is less than 1%. So this is, the martingale theory was initially developed for gambling. So this is the martingale inequality. And almost all the result I know for safety verification for stochastic system relies on this martingale inequality. So normally what they do is you develop different method to different, we can call barrier function, which in the meantime has to be a super martingale. Then you use this martingale to quantify this probability for the system to stay safe. So one limitation of this method is it's almost impossible to design a barrier function which is a super martingale in general, especially when the system is very complex, the obstacle is very complex. It's not scalable. So our method relies on martingale inequality, but in a very different way. So our strategy is again the separation strategy. So but now we rename this to set illusion, but it's the same idea. So what we do is we want to certify the safety of the stochastic system, right? So we know the stochastic system, the trajectory is going to fluctuate around the deterministic system trajectory, right? So if I can make sure two things, if I can make sure the deterministic trajectory stays in a smaller set, which is, there are many tools you can use to make sure this is the case, okay, in this set. Then if you can make sure the trajectory between the stochastic system and deterministic system is going to stay in a tube. So here I emphasize tube is because I want to make sure the trajectory, the entire trajectory stay in the tube. It's the space-time tube. So it's a trajectory level. It's not specifically for one time instance. Okay? So it's more or less the same as the reachability analysis, but the problem we would like to achieve now is just more complicated because we would like to bound the this probabilistic tube. So we would like to develop a tube along the deterministic trajectory such that the stochastic trajectory is going to stay in the tube, in the trajectory level with high probability. Okay, so which is a stronger result as what we discussed earlier. So this is the key. So it's against separation strategy, but it's in the trajectory level. Good. So this is the question we would like to answer. So to answer this, it turns out we need a slight generalization of the martingale, which I list the definition here, but I'm going to skip the detail. So basically, what we define is we define affine martingale, which is really just an affine transformation of the super martingale. So which basically means it's a stochastic process, but it's not a martingale. But if you apply an affine transformation, it's a martingale. Then you can use the trajectory level guarantee we discussed earlier. So this is a generalization, which can give you some type of a probabilistic tube. Okay? So what's interesting is that this average moment generating function we used earlier, which is this term over here, turns out to be a affine martingale. Okay? This is great. And because of this, we get this result. Okay? This is a very interesting result. It tells you the probability of xt minus xt less than this value, okay, for any t within your horizon. So this is trajectory level because it's for any t. It's greater than or equal to 1 minus theta. And this value, it can be computed explicitly. It's very similar to the one we got earlier, but it has an additional term t here, capture the entire horizon. Okay, so this is really the main result of this paper. So it gives you a bound of this probabilistic tube so that the trajectory is going to stay in the tube with high probability. And this bound is tight in some case. This,
clarify this 0 side.
yeah, when c is equal to 0, this becomes square root of t. This becomes t. Yeah. So the case when c equal to 0 can be understood in the limit. So yeah. And this actually will give some example here. So how good is this bound? Okay. So we did some simulation for the linear system because it's fast. So this is the when c is positive. This is the simulation you get. Okay. And this is the bound we get. I think this is 10 to the power minus, I don't remember, 10 to the power minus 4, but we simulate maybe 10K trajectories. So you see, the probability of the trajectory to cross this boundary is very small, and as expected because the simulation also verify what we have. And another thing is, you see, they are very close to each other, which basically means there's not much room for improvement. It's basically tight. And this is the case for the case when c equal to 0, okay? You have a bound which doesn't change over time, and then the trajectory is going to stay here. Even if you simulate longer, it's going to stay here, okay? And this trajectory level guarantee, this result is, you see, what surprised to us is that our result is for general nonlinear system, but even for linear system, this result was not known for the trajectory level. So the only result we know is the reflection principle, which is for the Brownian motion. So the only result we know is for one-dimensional Brownian motion, you can quantify the probability of a Brownian motion to cross some boundary. But other than that, even for general nonlinear system, there was no result, not let alone nonlinear system. Okay, so this is a very interesting result which can be of independent interest.
If c equals 0,
Yeah.
what's the dimension of the vector x?
I think this is, I don't remember, maybe 2 or 3. It's not
Does
1.
that matter?
It doesn't matter. Yeah, I mean, this is going to show up in the bound. Yeah, it's going to show up in the bound. Okay, so I think that's roughly the main part. So there's a small thing that just briefly mentioned that it turns out the bound we get over there doesn't work really nicely for c less than 0. Okay, which is weird, but we believe it's due to some proof technique, and we managed to find a way to fix that. Okay, you just need to introduce some additional term, so you get a bound which looks like this when c is less than 0. This is better, and also it's most likely it's tight. So this is what we get, but let's not worry too much about this small detail. But at the end, this is what we get. It's very similar to the reachability analysis, but this time is for trajectory level safety. So what you need to do is, okay, let's say C is the safe set. Okay, And you want to verify this stochastic system is safe in the trajectory level with high probability. So what you need to do is, over horizon, so what you need to do is you need to shrink your safe set a little bit by this ball. And this ball can be evaluated using this bound we just computed. Okay, then what you need to do is just need to make sure the deterministic system is safe with respect to this smaller safe set. If you can do that, you're good. That's roughly the general recipe. It again reduced a stochastic problem into a deterministic problem. That's basically the end of the technical part. So I just want to give you a few examples to see how this works. So here what we want is we have a dynamic system, okay, probably unicycle example. We have some obstacles, and I have a controller design. I want to verify if the trajectory, stochastic trajectory, is going to stay away from these obstacles with high probability. So what we did is we just make so this is the area of the safe set. I make the safe set smaller, right, which means I make the obstacle larger, which is like a buffer. So I make the safe set, the obstacle larger. Then if I can verify the deterministic trajectory does not intersect with this larger obstacle, then you can say the stochastic trajectory is going to stay away from this obstacle with very high probability. So that is a demonstration. Very simple to use. And you can also use this with a more complicated task, like a STL specification, which doesn't have to be safety, by the way. So here what we want is, we have a vehicle here. What we want to accomplish is we would like to reach this target at the end. And I want to avoid this obstacle. Here, actually, this is better. I want to reach here at the end. I want to avoid this obstacle. And I want to cross this area first before I reach the target. Okay, this is for the stochastic system. I want to achieve this with high probability. So what you need to do is you need to make this obstacle larger, and you want to make this target area smaller. And if you can make sure the deterministic trajectory cross this smaller set and reach this smaller set and avoid this larger obstacle, then you're good. You can do this for very general STL specification. So here, this is just a demo, okay? And you can also use this for control design. So what you do is, this is the MPC algorithm. So what you do is, you want to ensure safety in the MPC controlled system. So normally you would like to make sure the prediction is in some safe set. But if you introduce this randomness in the control design, it's going to create a lot of problem, especially computational-wise. So what you can do is you can choose a smaller safe set and then consider control design problem for the deterministic system and do this recursively. So this will give you a very good safety guarantee for the stochastic system. So I think these are just some examples. And these are the takeaways. So I think the main thing I want to deliver here is we provide a scalable algorithm for safety verification specifically for stochastic system. And our strategy is very simple. It's basically separate the stochastic disturbance and deterministic disturbance, and it reduces the stochastic problem into a deterministic problem. So that's the main message. It reduces the stochastic problem into a deterministic problem. Okay. So of course, the tool we develop can be of independent interest even beyond the control. So I think these are the papers we have so far, and I've covered the first two, but you can see the other papers if you're interested in that. And that's it. Thanks.
We have time for some more questions.
So the set erosion that you defined was based on time. But like, can you also translate that to a level of set erosion based on where you are in space? Like, so for example, this is like t equals 2.
Yeah, so that's a very interesting question. We have not done this analysis yet. So I think what we are talking about is more like a local analysis, which is something very interesting. You see, actually what you point out is the main restriction of this, at least this result for now, is we assume this condition globally for any x and b. And this is the major source of conservativeness of this algorithm, because very often the global contraction rate is going to be much worse than the local one. So there is a potential way of stitching different pieces, local contraction rate together to do some global analysis. If that happens, then yes, then you will see this erosion with different size at different time, different area, different state. Yeah, that's a very good question.
I have a basic question.
Mhm.
The notion of sub-Gaussian
Yes.
random variables introduces in terms of the moment generating function. What does it say about the higher order moments of the random variable, like third and higher? Does it say something that's
Yeah, it says because if you have this, it's like if you can bound the e to the power of something, right? If you expand the e to the power of something, then it basically says this random variable has to have finite order moment for all the order. Yeah.
and something about the decay rate? Is it similar to?
Yeah, it's the decay rate is very similar to Gaussian. Yeah, it's the most natural generalization of Gaussian distribution. But it includes a lot of distribution. Let's say any distribution with compact support is sub-Gaussian. Okay, that's very important. And I think most uncertainty we face in stochastic setting, they are sub-Gaussian in practice. I mean, there are some cases they are not, but
I see. And L here is the direction.
where?
What's the role of L, little l?
Oh no, because initially the sub-Gaussian is defined for the scalar setting. So this just says that if you have a scalar x, then you just bound e to the power lambda x. So for vector setting, what you need to do is just you do projection to every direction. You want to make sure that scalar is sub-Gaussian. That's the meaning of this definition. Actually. Yeah, it's just a definition.
Suppose I have a tight reachable set for the deterministic system. Do you know if the separation strategy gives you a tight probabilistic reachable set?
What?
Suppose like I knew the exact reachable set for the deterministic system.
Yes.
And then I add the stochastic disturbance. Do you know if the delta, like reachable set, is also tight?
Yeah, it's tight under this assumption. It's tight under this assumption. Under this assumption. So, which means that if this estimate, so that is related to an earlier question. So if my estimation of C and sigma are tight, then it's tight. So it's even tight in the sense that you cannot improve this further. But of course, normally this C and sigma, they are not tight. So that's going to be the problem.
Actually, a follow-up question. Is mu here, does it have to be just a normal Euclidean norm, or could you use different forms?
So that's a very interesting question. We believe something can be done for non-Euclidean norm, but so far we don't have the result for Euclidean norm. That's an interesting direction. Yeah.
In the case where you kind of handle the gradient in the negative C case by using union bound, can you explain more what you're doing there? Like what are the events that you're doing union bound over? Because you're doing continuous time, which makes me feel that
Where?
union bound is not necessarily that easy to use.
You mean the very end? Or this something I skip here?
Yeah.
Yes. So this is, if you understand the union bound, this is really what we realize is when C is negative, the martingale doesn't give you a very good result. But of course, the union bound cannot apply to continuous time system because it's just a combined discrete point. So what we found out is that we can discretize the system into different intervals, and for every interval we can apply martingale to get a bound. Then we can use union bound to piece them together, and this is going to give you a very tight result. Yeah, this is how we do it actually.
Okay.
Yeah. Yeah.
Yes.
So the optimal control problem, such as the stochastic DC that you showed,
Yes.
for the constraint that you end up with based on, I guess, the martingale, what does that look like in terms of, is that
It depends on C, right? I mean, the only thing you need is you need to have an effective algorithm to compute this. So if C is how would I say? So this is just a ball whose radius can be computed in closed form. So the C, this is the Minkowski sum. So which means I want to make this smaller. So I think if the complement of C is a union of convex set, then this is very easy to do. So which is normally the case, basically is let's say you have many obstacles, but each obstacle you convexify it as a convex set, then the complement is the C. Then in this case, it's very easy to compute C minus this. Yeah, it's very effective.
Other questions? All right, let's thank the speaker again.
Thanks.